In Episode 5, titled 1.1 Master Relational versus Non-Relational Databases for Fast Exam Decisions, the goal is to contrast major database types and the decision signals that help pick the right one quickly during an exam. The CompTIA Data Plus exam, referenced by DA0-002, often expects a candidate to recognize what kind of data problem is being described and which storage model best supports it. This is not about memorizing brand names or arguing that one database style is always superior, because real systems are chosen to fit constraints and workloads. Instead, the focus is on recognizing patterns in question stems, such as stability of data structure, need for strict consistency, and the kinds of queries that must run reliably. When those signals are clear, the right answer often becomes obvious without overthinking. A relational database can be defined as a system that organizes data into tables with enforced relationships, typically described using keys that connect one table to another. Each table is a grid of rows and columns, where columns represent defined fields and rows represent individual records, and the model expects those fields to follow consistent types and rules. Relationships between tables are enforced through constraints, such as primary keys and foreign keys, which are designed to keep references valid and prevent certain classes of errors. The language used to query a relational database is structured query language, SQL, which allows filtering, joining, and aggregating data in a consistent, declarative way. When a stem mentions consistent records, structured fields, and reliable joins, it is usually pointing toward the relational model. A non-relational database is best defined as a category of systems that store data using flexible models and formats that are not limited to rigid tables and enforced relationships. Many non-relational systems store data as documents, key-value pairs, wide columns, or graphs, and each style is optimized for particular access patterns and scale requirements. Flexibility often means the shape of data can vary from record to record, which can be useful when the information being stored changes frequently or arrives from diverse sources. A common umbrella label for non-relational systems is not only SQL, NoSQL, which signals that the storage approach is not centered on traditional relational tables and joins. The exam rarely needs deep product-specific knowledge, but it does reward understanding of why these models exist and what problems they solve. When a STEM emphasizes varied formats, evolving fields, or high-scale distribution, it is often pointing toward a non-relational approach. Relational strengths align naturally with transaction-heavy systems and consistent records, where correctness and integrity matter as much as performance. Transaction workloads often need guarantees that updates are applied reliably and that related records stay synchronized, especially when money, inventory, or compliance-relevant records are involved. The idea of transaction integrity is often described using atomicity, consistency, isolation, durability, ACID, which captures the expectation that updates happen as intended even when systems are busy or failures occur. Relational databases also excel when data is naturally structured into entities and relationships, such as customers, orders, and products, where each entity has a stable set of attributes. The ability to join tables on keys allows information to be kept normalized, meaning repeated facts can be stored once and referenced cleanly. When a STEM emphasizes accuracy, consistency, and controlled updates, relational is often the best fit. Non-relational strengths align naturally with scale, distribution, and changing shapes, where flexibility and throughput matter more than strict enforcement at write time. When data arrives in many forms, such as clickstream events, logs, device telemetry, or semi-structured records from multiple applications, forcing it into a single rigid table design up front can slow ingestion and create constant schema rework. Non-relational systems often allow horizontal scaling, where capacity increases by adding nodes, which can support very large data volumes and high write rates. Flexibility also supports rapid feature evolution, where new fields can appear in some records without requiring a table redesign before data can be stored. The trade-off is that consistency rules, and relationships may not be enforced by the database in the same strict way, so the application or data pipeline may need to carry more responsibility. When a STEM emphasizes massive volume, rapid change, or varied structure, non-relational is often the intended direction. Schema on write versus schema on read is a useful contrast because it describes when structure is enforced and when it is interpreted. Schema on write means the data's shape is defined and validated when it is written, so records must match the expected fields and types before they are stored. That approach fits well with relational designs because it protects downstream queries by ensuring data is cleanly structured and predictable. Schema on read means data can be stored in a more flexible or raw form first, and structure is applied later when data is read or analyzed. That approach fits many non-relational and data lake patterns where the priority is capturing data quickly and deciding later how to interpret it for particular questions. The exam often tests whether a candidate can recognize which approach reduces risk for a given scenario based on stability of the data shape and the need for reliable, repeatable reporting. Joins versus document nesting is another key comparison because it highlights how different models assemble related information. In relational systems, joins are used to combine rows from multiple tables based on matching keys, which allows data to be stored once and reused across many queries without duplication. In document-oriented systems, related information is often nested inside a single document, which can make reads faster for common access patterns because the needed information is already packaged together. The trade-off is duplication because nesting can repeat the same fact in multiple documents, and repeated facts can drift out of sync when updates occur. Joins require planning and can be expensive on very large datasets, but they preserve single sources of truth and support flexible querying across relationships. Nesting can reduce join cost, but increases the risk of inconsistent copies. So the best choice depends on the query patterns and the tolerance for duplication. A sales order example makes these trade-offs feel real because sales orders have both stable structure and clear relationships. In a relational model, a customer table can hold customer details, an orders table can hold order headers, and an order line table can hold individual items with keys connecting the pieces. That design prevents repeating the customer address on every line item and prevents repeating product details on every order, while still allowing queries like total spend per customer or top products by region. In a document model, an order document might include customer information and nested line items in one package, which can make it fast to retrieve a complete order for display or shipping. The cost is that customer details might be duplicated across many orders, and if the customer address changes, older orders may not reflect the update unless a deliberate update process exists. When an exam STEM describes order workflows, the decision often hinges on whether the system prioritizes transactional integrity and consistent updates or rapid reads of packaged documents at large scale. Modeling mistakes often show up when facts are repeated unnecessarily across tables or documents, and those mistakes create inconsistency and confusion in reporting. In relational design, Repeating the same fact across multiple tables can violate normalization and make it hard to know which value is correct when a conflict appears. In document designs, repeating a fact across many documents can create drift, where some copies get updated and others remain stale. A common mistake in sales data is storing product prices in both a product table and within each order line without clarity about whether the price is the current catalog price or the price at the time of sale. Another mistake is mixing attributes that belong to different entities, such as storing customer demographics inside an order line record, which makes aggregation confusing and increases storage cost. The exam often tests whether a candidate can recognize when duplication creates risk and when it is an intentional denormalization for performance. Indexes are important because they can make queries dramatically faster, but they also have costs that show up in performance and storage. An index is a data structure that helps a database locate rows or documents quickly based on specific fields, much like a book index helps find topics without reading every page. Indexes help when queries frequently filter or sort on the indexed field, and when the database must respond quickly under load. Indexes can hurt when there are too many of them, because every write may require updating multiple index structures, which increases latency and resource consumption. Indexes can also be less effective when they are placed on fields with low selectivity, meaning many records share the same value, because the index does not narrow the search much. Exam questions often probe this trade-off by describing heavy write workloads, changing query patterns, or storage constraints that make indiscriminate indexing a poor decision. Graph databases deserve separate recognition because they are non-relational systems optimized for relationships and path queries. In a graph model, entities are represented as nodes and relationships are represented as edges, and queries often ask about how things are connected through multiple hops. This is useful for scenarios like social networks, recommendation systems, fraud rings, or access relationships, where the central question is not just attributes of a record, but the structure of connections between records. A graph database can answer questions like shortest paths, common neighbors, or influence patterns more naturally than a relational join chain in many cases. The exam signal for graph tends to be language about networks, paths, connections, or traversal, especially when the depth of relationship matters. Recognizing that signal helps a candidate choose an answer that matches the query style rather than defaulting to tables or documents. The best database choice can be summarized as choosing based on the queries needed, the expected growth, and the stability of the data shape. Query patterns matter because they determine whether joins, nested reads, wide scans, or path traversals dominate the workload. Growth matters because it determines whether scaling will be mostly vertical by strengthening a single system or horizontal by distributing data across nodes, and that choice affects complexity and cost. Stability matters because stable, well-defined structures benefit from schema-on-write enforcement, while changing or varied structures often benefit from schema-on-read flexibility. Governance and integrity requirements matter too, because strict consistency and enforceable constraints reduce risk in transactional environments. When these factors are read from the stem, the exam question becomes less about preference and more about matching a tool to a job. To make the contrast easy to remember under time pressure, 3 quick contrasts can be held in mind as reliable signals without turning them into a rigid rule. Relational tends to fit stable structure, enforced integrity, and joins that support many query shapes, especially in transaction-heavy scenarios. Non-relational tends to fit flexible structure, large-scale distribution, and access patterns that favor packaged reads or specialized models like graphs. Schema timing often separates them, where schema on write emphasizes structure at storage time and schema on read emphasizes structure at query time. These are not absolute, but they are useful because they map directly to the kinds of constraints that appear in exam stems. When the signals align, the correct choice usually stands out. To conclude, fast exam decisions about databases come from recognizing decision signals, not from debating technology in the abstract. Relational databases are tables with enforced relationships and strong integrity, while non-relational databases use flexible models and formats that support scale and changing shapes. Schema timing, joins versus nesting, indexing trade-offs, and recognition of graph use cases all contribute to accurate choices when stems describe real constraints. The sales order example shows how the same business problem can be modeled differently depending on whether consistency and updates are central or whether packaged reads and scale are central. One practice choice to make now is to take a few everyday scenarios, such as orders, logs, and relationships, and speak a one-sentence justification for which database model fits and why, using the signals of structure stability, query pattern, and growth expectation. That single habit builds the reflex the exam is designed to reward. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.